In Module 4, you will hear from Dmitry Beryoza from the IBM X-Force Ethical Hacking team about a deep dive on one particular vulnerability, SQL injection. You will also review the OWASP SQL injection prevention cheat sheet. Are you ready for the challenge?
In this video, you will learn to describe the nature of various injection attacks and their prevalence on the threat landscape.
My name is Dmitry Beryoza. I'm a member of X-Force Ethical Hacking team. And a little bit about what we do. We do penetration testing of security products. We test products before they are released to customers. And for those who don't know, penetration testing is a type of security testing where tester or QA person acts as an attacker, as a hacker. So we use very same techniques and tools as the bad guys out there use to attack customers and products. And that helps us find security holes, and we report them to development, and they get fixed before the products are released. And in these presentations that we do, we show you a lot of examples that we see in real case scenarios out there. And hopefully, with the recommendations that we give, you would be able to both address and prevent security bugs in your software. So let's get started. Injection flaws, if we give a definition, they usually allow attackers relay malicious code through the vulnerable application to another system. Could be operating system, could be a database server, LDAP server, and just pretty much any component that accepts scripting as input. As you can see from this chart, they're fairly common, but what makes them special is that usually they're rated as high issues, top issues, and they're extremely dangerous. And in the worst case scenario, they may allow full takeover of the vulnerable system. You may be familiar with OWASP Top 10 list. It's an open web application security project, and it gives you a list of most common security vulnerabilities that afflict web applications. As you can see, from year to year, from previous version in 2013 to the current version in 2017 of the list, injection vulnerabilities are at the very top of the list. They're considered as the most dangerous type of vulnerability out there. There's also Sense Top 25, a list that you may be familiar with. And here you can see it's the same picture. Positions 1 and 2 are taken by SQL injection and OS command injection. Pretty much there's agreement throughout the industry that these are the most dangerous types of vulnerabilities out there. Injection vulnerabilities, we hear about them in the news constantly. They made possible some of the most dramatic hacks in recent history. The one you probably heard of last year was Equifax hack, where hackers used this type of vulnerability to leak data of, I think, 150 million US and Canadian citizens. That was truly massive. It probably even affected people on this call. Another example is a hack of TalkTalk, which is a British telecom company. Records of 157,000 customers were exposed through SQL injection. And if you read through news, you see these types of vulnerabilities come up very often. And the end result of these types of leaks are lots of customer data being leaked, personal user information being leaked. They're really, really dangerous.
In this video, you will learn to describe OS command injection attacks and the operating system flaws that allow them to occur. Explain why your applications should not execute OS commands, but use library functions instead. Explain why it is important for applications to run under the least possible privilege level.
So let's start with the OS command injection. OS command injection is abuse of vulnerable application functionality that causes execution of OS commands that are specified by the attacker. No one operating system is immune to it. It can really happen on any operating system, on Linux, Windows, Mac, because the vulnerability is really not in the operating system per se. It's the vulnerable application that makes it happen. And these types of vulnerabilities are made possible by lack of input sanitization and also by unsafe way in which developers often execute OS commands. Let's look at the concrete example. Let's say you have an application where you, as one of the types of functionality that you support, you manage log files. And log files are stored as real files on the operating system. And let's say we have an interface here where we'll list log files and give users ability to view by clicking on the log file and to delete. There is a little delete icon next to each individual log file. So sounds like a fairly common scenario. Let's assume that delete command is sent as a post request when you click on it. And of course, we need parameters to send to the server. And in this particular case, we send action, which is delete, and we send the file name. And assuming that Java is the implementation language, it's very likely what's happening on the back end is the exec function from the runtime class gets executed, and we send the file that was specified with the full path to a remove command to the shell interpreter. Those of you who are familiar with Linux should recognize this pattern. Those who are not, this is basically calling a shell interpreter and passing an operating system command line command to it, which rm is the command to delete the file. So in the end, what gets executed by the operating system is this line at the bottom, the shell interpreter with the parameter and a command in double quotes. So what's the worst that could happen in this scenario? Because application user essentially specifies the file name, and we assume that in our application we have no defensive code to verify that that file parameter is correct, attacker really can pass anything as that parameter. And in this example here, attacker could specify a simple as a system library, for example. You notice the ... convention. So in this case, we're actually attacker tells the system to travel up 3 folders and then down to the lib folder and then delete as system library. If there are no protections in place, this command that was originally intended to delete log files will actually delete an important operating system library, causing denial of service. Your server will not be operational after that point. That's pretty bad. A regular user of your application just basically crashed the server. But something else can also happen. The attacker can actually use Linux command syntax to inject another operating system command, which is much, much worse. So in this particular case, the text in red is the text that's supplied by the user or the attacker. And they say that, let's say the file name is X. It's not really relevant what the actual file name is, because there's a semicolon there. And that notation means that when we're done executing the remove command, go ahead and execute something else, whatever comes after the semicolon. Semicolons in Linux used to separate or chain together multiple OS commands. And in this case, the rm-rf / command actually on many systems would cause deletion of the entire file system, which is as bad as it gets. Operating system commands, command injection can lead to all kinds of bad outcomes. You could have full system takeover. You could have denial of service. Attacker could leak sensitive information, passwords, cryptographic keys, user personal information, confidential business data. Attackers could move to other systems. They could use your system once they've taken over it. They can move to other computers on the network. They can use it as a launching pad. And as we know, now the botnets and crypto mining are very popular forms of abuse that could happen as well. As soon as you give an attacker a way to execute an operating system command, they could do pretty much anything they want on that machine. So it's as bad as it gets. It's a game over type of event. How do we prevent this? So the first recommendation is not execute OS commands, which it sounds funny. I'm not trying to make a joke here. Executing OS commands is a tool that in most cases is too heavy for the job. There are more lightweight ways of doing things, and by adding OS command execution into your application, you're adding this very wide attack surface that, if you're not careful, can easily be abused. Often OS commands are introduced as a quick fix. So let's say you want to delete the file, but you don't want to figure out how to properly do it in the language that you're writing in. So you think, well, let's just run an OS command. It'll be quick and easy. And you essentially you let the operating system do the heavy lifting. But as we saw in the example before, if you're not careful, a destructive OS command may slip in and cause a lot of damage. So we recommend that when you're faced with a case like this, it's best to resist the temptation to run OS commands and instead use the functionality built in to your language you're using, or use third-party libraries. And here are some examples. If you want to remove a file, there's a function for that in Java built in. If you want to copy a file, same story. And there are examples of that in Java and in other languages. In most cases, you can avoid running an OS command. And by using the library functions, the big benefit of that is that you significantly reduce the attack surface. If you run an OS command, somebody can specify any command they want. But if you are using a library function to remove a file, your attack surface narrows dramatically, and it can only be abused to delete a single file elsewhere in the system. And we will show later on how to protect against that. But you can see that it's now far less dangerous. So the second recommendation we would give is to run at the least possible privilege level. We often see applications run as super user, as root user, and in vast majority of cases that is not necessary. And the problem with that is that if attacker does abuse your application functionality, if that application runs at a very, very high level of privileges, the attack can do a lot of damage. So if, let's say, if you are allowing it to delete a particular file, if an application runs as a root user, it can delete all kinds of important operating system files. But when it runs as Tomcat user, for example, that set of files that can be deleted narrows significantly, and far less damage could be done. And this recommendation, running at the least possible privilege level, helps in case of many other vulnerabilities, not just injection.
In this video, you will learn to describe additional OS command injection attacks, explain why commands should not be run through the shell interpreters, explain why it is important to use explicit paths when running executables.
The next recommendation is to not run commands through shell interpreters. You may be familiar with shell interpreters like sh, bash, that's on Unix, cmd, and PowerShell on Windows. When you supply your command, that let's say your business logic requires you to run an OS command, so you have no choice, you have to do it. If you run it and supply it as a parameter to the shell interpreter, then that also gives attacker extra power, because, for example, they could chain commands. They could, as the syntax I showed earlier with the semicolon, you could chain a number of commands in there, and the attacker could download malicious code, could delete files, could create web shells, do all kinds of damage. But if you run the command directly without passing it to the shell interpreter, then a whole set of shell syntax, such as semicolon, pipe, ampersand, backquotes, $, all that syntax that's introduced and understood by the shell interpreter is no longer valid, because you're just running a single command, in this case, a remove command, and you're passing in a file to remove. So this command that you see here, the second command on the slide, will actually fail. It will not work, because the semicolon will have no meaning to the rm command. Note that even if you do that, there's still danger of doing additional damage. You could not only manipulate the single parameter, but you could add additional parameters to a command that you're running. So here, in this example, we're running an nmap application to scan a particular IP address. However, if attacker has control of the input, they could specify additional nmap parameters. And in this particular case, it would cause Nmap to write a log file to a particular file that you specify. However, if it's running as a root command, there's a possibility that this would actually overwrite an important system library. So bad things still could happen. It's just the attack surface is reduced. You're no longer dealing with the full set of syntax that shell interpreter supports, but rather concentrate on a single command. Also, something to keep in mind is that another example that we often see is that you may execute a single command, particular, let's say a shell script, but inside that shell script, there could be something in those commands that could trigger OS command execution on the parameters that are passed in. So even though you're running something directly, not involving shell interpreter, there's still a chance that something could happen inside the script that you need to watch out for. And you have to scrutinize how you operate on the input that user supplies so that a malicious command is not executed inadvertently. The next recommendation is to use explicit paths. And applications are found by the operating system and executed based on system path settings. And there is a type of attack where if there is a folder on the system that's writable to a general user, and you have multiple users using the machine, and that folder also exists, is referenced in the path before the folder containing the executable you're trying to run, what the attacker could do is, if they have a low privilege account on the system, they could log in and they could drop a malicious version of the application, in this case in Nmap, in the folder that's under their control and that appears in the path before the regular folder where Nmap lives. And when we execute command without the full path, just say Nmap and then the IP address, that malicious executable will be run instead of the one that we intended. So to protect against it, it's best to reference all the executables that you run by their full path. That way there is no ambiguity and the right executable will be loaded. And by the way, the same recommendation applies to another type of attack called DLL hijacking, because the same thing applies to DLLs and shared libraries. Attacker could drop a malicious version of a shared library or a DLL into the folder that they control that appears in the path, and that would be loaded before the valid version of that same binary file.
In this video, you will learn to describe additional OS command injection attacks, explain why it is safer to use some functions over others, explain why it is safer to modify user input before execution, explain why it is safer to sanitize user input using whitelists and not blacklists.
The next recommendation is to use proper functionality when running OS system commands. So we started with not running OS commands at all, and we sort of going down the line now, assuming that you have a real business need to run OS commands, and we're trying to tell you how to better write your code and execute those. If you still have to execute those commands, but execute them correctly. So in Java, for example, there are different ways of running an external command, and one way that's very common is to just build a full string of the executable and the parameters and execute things like that. With that, injection is more likely than with another type of function, the one that takes a string array. And the reason for that is that the second variant already kind of gives the operating system the command and the parameters pre-parsed as individual strings. So if attacker has control of, in this case, IP address parameter, and tries to jam more stuff into it, go from one parameter into many, with the second variant of the function call, they won't be able to do that. They will not succeed. But with the first variant, they might. So when you run OS commands, please evaluate what's available and use the safest functionality that's available. The next recommendation is, if possible, do not let user input reach the place where you execute the command unchanged. And what I mean by that is, you could deal with different entities that the OS command will be operating on in the UI as symbolic IDs. So instead of letting users specify a particular file to delete. You could have a numeric ID that corresponds to that file, and when the parameters come in, that ID is passed in. And inside your code, you could use a translation table to convert that number to a real file name and then delete the file. And this is much safer because now attacker cannot really specify anything malicious as that parameter value. If they specify something that does not exist in that internal mapping table, then you can just reject that request with an error. They won't be able to sneak any operating system commands or any malicious parameter in because that parameter will not be recognized. It's another good recommendation to follow. Sanitization, that's kind of a universal advice that we give. The users communicate with your application through parameters most often. So carefully sanitizing them with strict whitelists and not blacklists. If you saw our previous talk, we talked about the importance of whitelists. I'll quickly mention it. With blacklists, we mean a list of input that's known to be dangerous, and in your logic, you may look at it and see, well, does the parameter that was passed in, does it match any of the bad stuff on this list? If it doesn't, let it through. The problem with that is that it's incredibly hard to build a successful blacklist, and I'll give some examples shortly. Attackers are usually very inventive, and there's a link in the slides. If you click on it, there are lots of examples there of what at first seems like a good blacklist can be easily bypassed by an inventive attacker. So instead of using blacklists, please use whitelists. And by whitelists, we mean a very tight, very controlled list of what's allowed, and all other inputs should be rejected. That way, you're dealing with a known entity that's fairly small. You can analyze it, and you can really come up with all the use cases that the user could specify and see if they're dangerous or not. So just some examples here. These are actually real life examples that we saw in the applications that we tested. So let's say we have in our application code a blacklist of, we reject things that contain semicolons, ampersands, and pipes. The attacker could still sneak in an internal OS command that's surrounded by backticks. That's a valid Linux syntax. Let's say you add backticks to the blacklist. There's another syntax with a $sign. You could blacklist spaces. Let's say, say my file name should not contain any spaces because that's an indication of something malicious going on. There is a way in the operating system command syntax to replace spaces with a value from a known system variable that contains a space. So institution here acts as your space. So they could still sneak something in. You could say that, well, I'll enclose the value in double quotes and then also escape double quotes in the value. That should be secure. Unfortunately, there's a way around it as well. It's a bit of a more complicated example, but if you look closely, it's this last line in the table. The red input is what the attacker would send. So they would actually send in the double quote already escaped with a backslash. And because your application would escape the double quote anyway, the single backslash turns into double backslash. That's one real backslash. And the double quote goes unescaped. And that allows the attacker to chain an additional set of commands. As you can see, attackers can get really, really creative. And you usually don't have time and cycles to think about all these very complicated cases. So it's best to use a whitelist, and at the regular expression whitelist at the bottom would have taken care of all of these cases easily. You just accept file names that are alphanumeric. There's a possible dot in there, and that's it. So none of those cases would work if you were to use this whitelist. So what are the key takeaways? Try not to use OS commands. There are much safer ways of executing functionality that's usually done in the context of OS command. So only use OS commands if absolutely necessary, if it's dictated by your business logic. Try to run your code with least possible privilege. Do not run OS commands through shell interpreters. Try to run them directly. Use explicit paths when running applications and shared libraries. Try to use safe library functionality. There are usually multiple variants, some safer than the others. Try not to let user input reach the point where OS command is executed unchanged. It's better to try and use generated IDs and try to sanitize all user input with whitelists.
In this video, you will learn to describe SQL injection and what makes an attack possible. Describe common types of SQL injection, including error-based, union-based, blind injection, and out-of-band.
So let's go to SQL injection. So just as OS command injection, this is abuse of vulnerable application functionality that causes execution of SQL queries. So it's queries executed by database systems. Possible in pretty much any SQL database. And the main mitigation is also input sanitization. So let's look at an example. Let's say we have a login dialog. You probably have something like that in the application you are developing. And very often, what we often see in the code is that there's, in this particular case, a Java statement to piece together a SQL command and just directly embed username and password in that SQL statement. So when user is found in the database that matches that username and password, we'll let the user in. And when the input is benign, then everything works fine. However, let's see what happens if an attacker injects something malicious. So at the very bottom, there's a statement here that actually does not specify any password. So password is left blank. But the username is kind of interesting. It starts with a single quote, then there's an or statement, or 1 equals 1. Then there's a semicolon and there's a dash dash. So let me go through that to explain what's going on. So as you can see in the SQL syntax, the value is often surrounded by single quotes. So what the first single quote here does, it actually closes the value for the username. And what happens next is attacker adds a Boolean clause or clause, and then an expression 1 equals 1. 1 equals 1 will always be true, right? And if you're familiar with Boolean logic, if there's something or truth, then the result of that expression is always true. And the rest of the syntax is the semicolon just separates different SQL queries. You could chain them using semicolons, and dash dash in many SQL flavors is a comment. So it basically comments out the rest of the line. So the quote and pass equals quote quote is actually ignored. So essentially, an attacker has turned our SQL query into the one that finds any user in the user's table, does not check the username, does not check the password, and just blindly lets people in. So you could, with this very simple piece of text, bypass your login dialog on a vulnerable system. And we've seen examples of that. So what are the dangers of that? Well, first of all, the first one that comes to mind, bypass of authentication mechanisms. Then data exfiltration. Exfiltration is a kind of a, I guess, military term. It comes from ability to extract something. So attackers can steal data. That's in a lot of hacks that you read about in the news, they steal customer data. That's how it's done, by using SQL injection pretty often. You could even execute OS commands. In some variants of SQL, you could specify an OS command to run. So if you're able to somehow inject this SQL statement here, copy, select one to program, and then the OS command, you could get that OS command executed. And also, there's always vandalism or denial of service attacks. You could, for example, tell the SQL server to delete the table, and your system is dead after that, pretty much. So with one simple request that contains the SQL injection command, you could bring the whole system down to its knees. And there's an example down there for that shows the use of semicolon to separate statements. So you could do not assume that if they can inject something malicious in your query, that they could not execute other queries as well. There are ways to chain queries together and execute nested queries as well. There are many variants of SQL injection. There's error-based, so attacker may look at how your system behaves based on the error messages that it gives back. So giving back, private information in the database error directly to your application user tells them a lot about what's going on the back end and allows them to tailor their commands. There's union-based SQL injection. So, for example, this is an interesting case. This is how data actually could get exfiltrated from the system. We have query here that gets the name and some text from the log file, where there's a particular date that's used as the filter, and that date in this case is under the control of the application user. If there's no input sanitization in place, they could specify more than just the date. They could add a union clause to that query, select, let's say, username and passwords from a completely different table, from a users table, and that would be added to the output. So this way, when they abuse the functionality that loads data from the log, this functionality will return names and text from the log for a particular date, and appended to that will return usernames and passwords, which is something you don't want to happen. There's also blind injection. This is an interesting one because sometimes people say, well, yes, I run SQL queries, but no data is returned to the user. So what's the big deal in this case? There are actually many ways to do injection blindly and guess what data is just by the behavior of the system. There are two main types, which are Boolean based, which is you run a query, and as you tweak the parameters, there could be one or two possible responses. And because of how the system responds, you could little by little guess what the data is. Or there could be time-based. For example, you could sneak in a delay into your query execution so that if data is of certain type, it does not delay, and if there's something else in the content, it does delay. So it's probably easier to explain using an example. In red here, we have a SQL expression that says that if password starts with the letter A, then sleep for 10 seconds. Otherwise, return false. So when the attacker executes this expression, if they guessed correctly, the response will come back 10 seconds or 10 milliseconds, I'm not quite sure, but will come back delayed. Whereas for all other characters they try, there will be no delay. So by being able to execute, let's say, 26 queries to account for all the letters in English alphabet, they would be able to, at the end of that, they will be able to know the first letter in the password. So if there are no restrictions on the number of queries you could execute, you could write a script that tries letter in the password one by one, and for each letter, go through whole range of possible values, and that way you could discover the password without ever getting data output to the screen from the database. So you have to be careful about that. Even if your application does not return data, attackers, if they can sneak in SQL injection, they could get to the contents. There's also out-of-band SQL injection where they could trigger requests to other sites and exfiltrate data through some other ways, not even through your application, but through other channels.
In this video, you will learn to describe how to prevent SQL injections, including use prepared statements, sanitize user input, do not expose native database errors to the user, limit database user permissions, use stored procedures, use ORM libraries.
How do we prevent it? So the number one recommendation for prevention is using prepared statements. So you can see two different patterns here. The first one is the original one that we saw, and it's easy for the attacker to inject something that they want to play with the structure of the query. However, if you use prepared statements, and you'll notice that parameters are now replaced with question marks, what prepared statement is really like a compilation process. So the logic takes this query, compiles it into internal representation, and now its structure is sort of set in stone. And no matter what parameters are passed in, they're not going to be interpreted as part of the query. They'll always be interpreted just as parameter values. So nobody would be able to come in and sneak in another, where clause or sneak in a union query, because once the statement is prepared, it's set in stone and cannot be modified. So now by using that, we've mitigated the SQL injection risk. There is something to keep in mind here, however, that we do see people sometimes using prepared statements, and yet, I guess, not fully understanding how they work, because we see a pattern at the bottom here. So there's a prepare statement, and yet appended at the end, there's still something that came from the user. So you're compiling the statement, but you're sort of baking possible malicious input into your prepared statement. So please don't do that. If you prepare a statement, it should be a constant thing. It should not be controlled by any user input, or at least no user input should be inserted at the preparation stage. Just as with OS command injection and many other types of vulnerabilities, sanitize user input. Expect all input to be malicious. That should be your modus operandi. And only use restrictive whitelists, not blacklists. And again, it's also a good idea not to maybe let the input reach the database directly, maybe use mapping tables to kind of have that extra layer of protection. Another recommendation is to expose as little information as possible in your error reporting to the user. Very often, attackers would look for error messages because they give them all kinds of clues about what's working on the back end. So let's say I start at testing the application, and I don't know what database system it goes against, and now I see this error. So let's say I sent a whole bunch of input. I see an error that's very helpful to me. First of all, it tells me it's using MySQL. So that dramatically reduces the type of things, rather than reduces, narrows down the type of things that I could try against this particular application. And also it gives me hints about the query structure. So I now start thinking about what's the best way to inject things in this particular case. So please do give as little information as possible about the underlying database technology to the end user. Detailed error messages belong in internal log files that could be reviewed by engineers, but the end user really shouldn't care about these types of errors. Do not make attackers' job easy this way. Same recommendation as for OS command injection. Limiting database user permissions is a good idea. If I'm a high privileged user, I could do a lot of damage to the database. Whereas if it executes as a low privileged user and only has access to certain tables, or better yet, has a read-only access, if your business logic allows that, please try to do that. Using stored procedures is also a good idea. They're also sort of kind of compiled and stored in the database engine. It's harder to abuse stored procedures with SQL injection. There was also a question asked about ORM libraries in the previous presentation. Object relational mapping libraries, they help mitigate SQL injection. They sort of create an in-memory set of objects that kind of map to your database structure. So it's harder for an attacker to come in with malicious syntax and modify that. And an example of that is a Java persistence API and implemented in many different products. One popular example is Hibernate. So it does help reduce the need for direct SQL composition, does help reduce SQL injection. However, with any tool, if you're not careful with what you're doing with it, you could still be vulnerable. In ORM tools, there are ways to hand piece the SQL statement together. And if you use that and use that insecurely, then we're back to the original examples that we saw, where an attacker can control the query that you're building and do damage. So if you're using ORMs, please use them correctly. So key takeaways: use prepared statements and do it correctly. Sanitize user input. Do not expose native database errors to the user. Expose as little information as possible to the end user. Please limit database user permissions. And it's a good idea to use stored procedures.
In this video, you will learn to describe other types of injection attack, including NoSQL injection, XPath injection, LDAP injection.
We still have a little bit of time left. So there are other types of injections, unfortunately. It doesn't stop with OS command injections and SQL injections, although those are the most popular ones. A lot of applications now use NoSQL technology, and you may think that the likelihood of injection is reduced there, and it is. However, even in NoSQL databases, there are places where you have expressions or little pieces of script that can be used. If you allow user input to reach that functionality unchecked, then injection can happen. So in this particular case, in MongoDB, there is a particular expression, this user type equals 3, which I've seen examples of something like this in real applications. Application authors specify this type of expression as a parameter that's submitted from the UI. But that gives me, as an attacker, control over the expression. And I could, instead of using a simple expression like this, I could inject something more dangerous. So at the bottom here, there's a piece of JavaScript that MongoDB does, interpret JavaScript or a variant of JavaScript, where I could do a denial of service attack. So here, it does a loop for a very long time, delaying the execution of the query. So the user of your application could essentially hang your application if no checks are in place. So be careful there, and do not assume that if you're using NoSQL injection that you are safe. Please review all the functionality that you're using and think about how it can be abused. XPath. XPath is a popular technology. XPath expressions operate on XML trees. There are sometimes examples of XPath using queries to search for login credentials in an XML document. And if it's not done carefully, then it could expose you to injection. So in this case, we have a search statement looking for a particular username and particular password. If the input is like that, it's fine, there's no issue. However, if attacker can inject another pattern that you're already familiar with from SQL injection, they could cause this query to find any user with any password and basically log you in. So be careful of that and sanitize your input in order to let something like this happen. LDAP, we use LDAP a lot in many of our products. And LDAP also has a syntax. So I think you can see the pattern developing. Pretty much anything with a syntax where you can specify an expression or a little script could be abused. So in this particular case, we have an LDAP expression that finds a user and password. And the ampersand says that it has to be both that user and that password in the LDAP directory. And again, if the input is benign, it'll work just fine. However, if an attacker sneaks in a malicious syntax that matches any user and plays with the expression so that the password doesn't really matter, so as you can see in red here, then if you rely on this expression to log in your users and you don't look at your input, do not protect it, you could let someone log in without username and password just by using this. And there are other types of injection. Our applications use all kinds of templating engines. Those are sometimes vulnerable, and there are many other technologies. And the recommendations for avoiding injection is pretty much similar across the board. So overall, just to kind of recap, try to use functionality with reduced scope. Only use the best tool for the job. Execute with least privilege. Use safe functionality that prevents injection. Do not let user input reach the critical resource unchanged as much as possible. And sanitize your input with whitelists, not blacklists.